So it's my pleasure now to introduce our second speaker, Dr. Jitendra Malik. Dr. Malik is joining us here today from UC Berkeley. He's a professor of electrical engineering and computer science at UC Berkeley and is one of the most well-respected researchers in computer vision and machine learning. And so it's an honor to have Dr. Malik here today. And Jitendra, welcome, and please go ahead.
Hello, can people see my screen? Okay, and I can hear me? Okay, thank you. Thank you, Serena, for your kind introduction. And I'm sorry I could not be there in person, but I will tell you for the next 25 minutes about some of the work that we are doing in my research group, which may be of relevance to the main topic of this, machine learning in healthcare. Going to be talking about observing, and as this video indicates, what do I mean by that? People from video, and be multiple people in the video stream. And what we want to do is to understand them in 3 dimensions, as 3-dimensional entities, and of course, moving and evolving and changing through time. So if we are able to do this effectively, there's a range of clinical applications, such as monitoring patients in the hospital or at home, biomechanics-based diagnosis, physical therapy for rehabilitation, and so on. But in my talk, I'm not going to emphasize the specific applications and really focus on the techniques and hope that the applications will be there for people to think about. Okay, so this is a classic and important problem. I myself have, and my students have been thinking about it and working on it for more than 25 years. I think this is one of my first papers on this space. And if some of you may be recognizing this sequence, this is a film which was made by MyBridge, which you could think of as the precursor to the first motion picture. And what he tried to capture was humans moving over time. He also did these studies for various animals. And our goal was to start from this video stream and build a 3D reconstruction of the person over time. And we could really do this. I mean, these are results which worked under very, very special circumstances, and this could not have worked in real images at that time. And we can think about the data available at that time. So we're talking about, say, 20 years ago, and the kind of video which was available, and this is perhaps exaggerated in terms of the quality of video that was available, but generally it was low resolution, grainy video, and one couldn't aim to do 3D reconstructions from that. This video at that time started to be used in surveillance applications, but I think for something very serious where you need more detailed understanding of humans, this was not going to work. But this is what video is today. So here we certainly have the kind of resolution, the kind of quality data with which we can hope to make detailed inferences of what every person is doing, identify their gaits, subtle changes in different people's gaits, and so on and so forth. So how do we do that? And what I'm going to talk about our journey in this process, and it turns out we can do a lot now. It's amazing how much progress there has been in the last 5-10 years with the advent of deep learning and the kind of computing and data resources that have accompanied this revolution. So I'm going to start by talking about the first task here, which is how to go from images to three-dimensional reconstructions of people. So we may have only one image of a person. I mean, in general, we'll have many because we may have a video stream. But even from a single image, we should be able to lift from 2 dimensions to 3 dimensions. So how do we do this? So for this, we need a model of the human body. And the kind of model which is very common in computer vision is what's called a simple model, SMPL model. It captures the geometry of the human body. And it's been built by scans of many people. And the idea is there is this beta vector, which captures in 10 dimensions the morphological variation of a human. So skinny people, tall people, plump people, short people, that kind of stuff is captured in the beta. Then we have the pose of the human body. So this refers to all the joint angles, the arm, the leg, upper arm, lower arm, legs, etc. So all the joint angles, right? So that's captured in this theta vector. And then these together give rise to the body. Of course, there's also the camera, which looks at this body. And notice that this misses out on some subtlety, right? This is basically a model of a skeleton with some skin and muscles on top of it. There's more subtlety to be captured, but this is a very good starting point. Okay, so what is our goal? Our goal, so these 85 dimensions, the combination of shape, pose, and camera, they define a body in an image. And what we want to do is to start from the pixels and recover these 85 dimensions. So that's the million-dollar question, how to recover these 85 dimensions from an image. And obviously the answer today is why not just throw a deep network at it? So the goal is we have some image, there's some neural network, and at the end, these 85 numbers, which will capture the shape and pose of the human body and the relationship to the camera. Okay. And then, of course, once you have the person in 3D, then you can look at him or her from any viewpoint. Now, this is the standard paradigm of supervised learning, but it turns out it is challenging. Because what do we need to achieve this? What we need are pairs. We need to have images and we need to have these 85 parameters. So but consider this image of this baseball player. We don't know the ground truth values of those parameters. What is the person's shape? What is the person's pose? So that's the problem. So there is some data which collected in the lab. Humans 3.6M is one example, where you bring people in the lab, you take photos, and you try to scan them in at the same time. But this data is never going to capture the variety of people in the real world. So this is the problem for us. We don't have paired 2D to 3D labels, which is the bedrock on which supervised learning works. So then there is, when you go from 2D to 3D, there is always the depth ambiguity problem, because there can be multiple 3D reconstructions, which can give rise to the same 2D image. So how do we deal with this? What's the solution? So the solution is that we don't have paired 2D to 3D labels, but we have a lot of unpaired labels. So we have lots and lots of 2D data. And then there is something that we can get human annotators to do, which is that on this 2D data of humans, we can ask an annotator to mark key points. So the key points could be left shoulder, left hip, right hip, left elbow, right elbow, and so on. So those are two-dimensional points that can be marked on two-dimensional images. And that's a powerful constraint, because whatever we guess of the 3D shape and body pose, it should be consistent in terms of its projection to two dimensions. And then we know something generically about humans, which we can obtain from 3D scans, which is essentially what is the space of the human body. Okay. And that we can acquire from 3D scans. So basically the goal is to explain the 2D data in the distribution of human shapes. So with this general idea, and now I'm going to skip the details. There's a paper published at CVPR 2018, so it's now 4 years old. We can start from some image, and there's a network which is going to output the pose, the shape, and the camera, and that's a reconstruction in some way. And what's the test here of whether this reconstruction is a good reconstruction? The test is that when you project it back to the image plane, then it should be consistent with where we thought the 2D key points were. And the 2D key points in these images are annotated by human annotators. So this is one constraint. So that's the loss which is indicated here. You project and then you match in the 2D space that you've got the key points at the right place. If you think that this is the human, then the human's right elbow should be where an annotator has marked the right elbow in this 2D image. But if you just do this, you get some horrible looking results. So you get these monsters. So what's the characteristic of these monster reconstructions? The 2D key points are at the right places. But what we have reconstructed is not a valid human shape. So this is because we have not yet exploited the constraint of how human bodies are organized. And that we can do by using a discriminator. And this is itself another neural network. So once we do this, the whole technique works. And basically, we can start from single images and reconstruct a 3D person. And to show off the 3D person, here you see what the person may look like from a different camera angle. And of course, since you have this 3D reconstruction of the body, we can actually paint the different parts of the body. So this is the head, and here's the torso, and here's the left hand, and left arm, right arm, and so forth. And note that with this reconstruction, we can predict even the parts we didn't see. Because from the visible, we predict the whole 3D body. And on the visible part, it will be consistent with what you see. And the occluded part will be consistent with some kind of a statistical guess based on prior distributions of how people sit and so on. Next, I'll talk about, so that's the single image clip. But of course, we typically have access to video data, and that enables us to do a lot more. So I'm going to talk a little bit about that. And this is called the tracking problem, because multiple people in the scene, and they can be hiding each, because there are objects in the scene as well. So, so this is the published earlier this year, and these are some of the results from that kind of a model. So what we are able to do is to fit a 3D body shape to every human, in spite of the fact that each of the humans may be partially occluded. And then over time, people are moving, and yet the colors indicate that we have kept track of who that person is. So how do we do that? And this is, again, a problem which has been studied for quite some time in computer vision. And for a long time, all the techniques were two-dimensional. And I think that it's much better to do everything in 3D. And today we have the kind of compute and data and algorithms that enable us to do that. So let me illustrate why 3D is better than 2D. In 2D, occlusion is hard to disambiguate. So when you have two people who come very close to each other in 2D, then the pixels overlap. But if we do the reconstruction in a three-dimensional space, then people never disappear. They can be hidden from the point of view of the camera. But in the three-dimensional space, they each have their separate lanes. They always continue to exist. Here's the second point. Look at this player. As he's running around, you will notice that he bends and so forth. So if you focus on the bounding box of the person, this is the standard building block of computer vision. We detect objects and we have a bounding box around them. At the level of the bounding box, it's changing all the time, right? It's shift, okay. And his appearance is changing. And so when we track in 2 dimensions, this is a source of noise. Right? The bounding box appearance changes rapidly. And the appearance, what happens if we think in 3D? So in 3D, what we think about is the color on the body of the person, 3 dimensions. So at that point, which is marked there, there's a part which connects to the guy's arm. So that will, where there we see some skin tones, and we see the guy's t-shirt, which has a certain color. And those don't change, even though he's changing his pose as he's running. So if we think about appearance as referred to on the 3-dimensional body of the person, it doesn't change that much. And in fact, in all these examples, that would be the same. Okay. And however, when we reason in 2D, it's changing constantly. So our logic was, okay, it's going to be a little bit more work to first lift to 3D, but in 3D, then we'll get the benefit of this invariance. 3D appearance is invariant to viewpoint and pose. So these are the two key insights. Occlusion causes no problems when we are in 3D space because the body continues to exist even if it's currently invisible from the point of view of the camera. And then 3D appearance is invariant. So based on this, we built this system, which was very successful in trying to do 3D reconstructions from video. So the starting point is that we have video and we can detect people. And again, there is now good technology for this. So we can detect people quite effectively in a variety of poses and appearances and clothing and all the rest of it. Then we extract features. And then we do some kind of spatio-temporal aggregation. Because the way we should think about video is that it's a spatio-temporal volume. And each person is sweeping out over time a chunk of that spatio-temporal volume. It's like a 4D space, 3D, the 3 dimensions of X, Y, Z, and the 4th dimension being time. And each person, as they move, they are sweeping out some volume in time. And we want to think of every person's volume in this way, every person's 4D volume in this way. And that's a goal of spatio-temporal aggregation. And then finally, we can do this reconstruction from which we can then extract more any attributes we desire. So let's look in a bit more detail. So we can start from images and we can recover all of these. We can recover the 3D pose. We can recover 3D location. What do I mean by 3D location? This is the X, Y, Z position of the person. Where is the person with respect to the camera? How far away? In which direction? That sort of stuff. And then we have appearance, and the appearance refers to, technically, it's what people call a texture map, because the body of the person is being modeled by these triangles corresponding to the mesh. And on that mesh, for every triangle, there's a color. So if it's on the guy's forearm, then it's going to look like this skin color. If it is on his torso, then it will probably be the color of his t-shirt. And this is going to roughly remain constant because somewhere during the middle of a run, the person doesn't go off and change his t-shirt. So we start from some image. And so this algorithm of ours is called HMR, Human Mesh Recovery. And from this, we can recover the pose and the location. But we can also recover the appearance, which is indicated here by this texture map. There's a standard technique in graphics where you have shapes which are captured by these triangles on the mesh. And then for every triangle, you have a color. So now when you render it, you get something which looks like the person. So we have these 3 things. So what is the aggregation and prediction problem? So we have to do the matching. So I have a tracklet accumulated over time, and now my new frame comes, and I have to know which pixels belong to the tracklet of person A, person B, and so forth. So what we do is we use the past to predict where the person is, what pose the person is expected to be, where the person is supposed to be, the location, as well as the appearance. And then we do the match and assign all the detections in the new frame to the best matches possible. So there's an appearance, there's a prediction of the pose of the body, there's a prediction of location, and then there's a prediction of appearance, and then we use that for doing the best match. So pose prediction is we know the pose of the person at previous time instance, from which we have this transformer. This is the most popular technology in neural networks these days. So we have a human motion and mesh recovery with which we can model, which can predict what the person would be at frame t+1. And this has been trained from previous data. And with this, we can try, and in fact, we can use that to predict a t+2 and so on. So this gives us what to try to match with at the upcoming frame. Position, we are looking at position of the body at various moments in time. And locally, we can model this as a line in three-dimensional space. And therefore, we have, again, a prediction of where the person will be at frame t+1. Appearance corresponds to the texture map of the appearance of the body. And that is basically computed by our algorithm. And what we are doing over time is capturing different parts of the body. So initially, you might see just the front, then you might see the back, and so on. So that information is being accumulated, but the model, of course, is that it's constant. So we know the appearance, we know the 3D pose, we know the 3D location, and now to match with the upcoming frame, you try to find the match which has the smallest difference in appearance, pose, and location. And we combine these differences, and there's some weights, there's some learning story associated with that, which I won't get into. So there is the aggregation over time, prediction at time t+1, and a comparison with the detections in the latest frame. Find the best match. Which of these is this person? And once we have assigned all those matches, then we have extended the track by one more frame, and then we just continue. And here are some of the results. So I've put this mask only on the head and shoulders of the person because just to avoid crowding the display. Here are examples which show that this technique works with many people moving fast and so on. And you can sometimes these athletes are hiding each other. Here's the example that I used to motivate the technique. So notice that he disappeared, but then we don't lose the track. Again, lots of people in this case at some exercise class or dance class. Here are examples of people doing other kinds of activities, and we have tested the algorithm in a very wide variety of situations. So the noteworthy point is people get temporarily occluded, but when they reappear, the color of the mask on their head is the same, which means that we kept track, and they were out of sight but not out of mind. Okay, here's another sequence, and yeah, there are standard data sets, and we have run it on many of these. And post track, Newport's, AVA, and basically algorithm wins by a very significant margin over previous techniques. And the main innovation here is that we switched from trying to do tracking in 2D to 3D, which is, I think, advantageous on many different grounds, and basically enabled us, if you look at some of the, this IDS means ID switches, where you, over a track, you lose the identity of one person, you associated them with a different person. And if the bottom two are both our techniques, there's a variation, but the main thing to look at is from 702, it's dropped to 541. So that's like a close to a 20% improvement, which is quite big. Okay, I'll in the remaining 5 minutes, I want to mention that this was the whole body, but we are not interested in the whole body, but just a part of the body to which we want to pay more attention. So this is paper which we did where we applied these techniques to reconstructing hand-object interactions. So that's the setup is like this. We have some image where people are interacting with objects. So in this case, we want to 3D-fy the hands, but also the objects. And we want to see the hand in relationship to the object, because this is a pretty common case that we are interested in. Okay. I think this picture shows the hand in 3D and the object in relationship. And we have a technique for that, which is based on doing a 3Dification of the human body. So the hand is as part of that. And we also 3D-fy the object pose. And then there is some joint optimization to be done, because obviously the hand should not penetrate into the object. The volume should be disjoint, and yet the hand should be in contact with the object. So by exploiting those kinds of constraints, we can develop this refined 3D reconstruction. And here are some more results of people in doing natural activity. And some more examples. So it's the same spirit, 3D all the way. And this enables us actually to do some research on how do humans use their hands. So for example, we have now tons of data of humans manipulating objects and what are the degrees of freedom. It turns out that if you do this kind of analysis, you can see that the first degree of freedom is, okay, let me see if I can show it on my hand, is this one. So babies, their first movement is with their hand grasp is this one, and then this is the second one. So you get that kind of principal component analysis just emerge from the data. And with this is data in the wild. I mean, people have known this for ages, but they've done this by collecting data in labs. And here we see this is what it is in the wild. And I'll end my talk here, and thank you so much for listening.